For centuries, humanity viewed the universe as a grand, intricate clock. We believed that if we could only identify all the gears and springs, we could predict its every movement. This mechanistic view, rooted in the precision of mathematics and astronomy, offered a comforting sense of order. The heavens themselves seemed to move with predictable regularity. Eclipses could be predicted, and the seasons followed a familiar rhythm. This perspective extended beyond the celestial. Early scientists and philosophers sought to apply the same principles to the natural world. Life itself, they believed, operated according to fixed laws. If we could unlock these laws, we could understand and control the world around us. This deterministic viewpoint permeated scientific thought for generations. It fueled incredible discoveries and advanced our understanding of the physical world. However, this neat and tidy picture of the universe would eventually give way to a more nuanced and awe-inspiring reality. The seeds of this intellectual revolution were sown by the very discoveries that seemed to confirm the clockwork universe. As we delved deeper into the intricacies of nature, we began to uncover a world far more complex and interconnected than we could have imagined. The universe, it turned out, was not a simple machine. Isaac Newton, a towering figure of the scientific revolution, played a pivotal role in shaping our understanding of the universe. His contributions to science and mathematics were monumental, laying the groundwork for centuries of scientific inquiry and discovery. His laws of motion and universal gravitation provided a powerful framework for explaining the movements of planets, the tides, and the behavior of objects on Earth. These laws were not just abstract theories, they had practical applications that could be observed and tested in the real world. Newton's insights into the natural world were revolutionary. He showed that the same principles governing the motion of celestial bodies also applied to everyday objects. Whether it was an apple falling from a tree or a ball rolling down a hill, the same laws were at work. Newton's work cemented the idea of a deterministic universe, one where cause and effect were directly linked. This deterministic view suggested that the universe operated like a well-oiled machine, with every part working in harmony according to fixed laws. Newtonian physics instilled in us a sense of predictability and control. It gave scientists and engineers the confidence to design and build complex structures, knowing that they could rely on the principles of physics to ensure stability and functionality. It suggested that with enough information, we could calculate the trajectory of a cannonball or the orbit of a comet with remarkable accuracy. This ability to predict and control the physical world was a powerful tool that had far-reaching implications. Newton's laws allowed astronomers to chart the paths of celestial bodies with unprecedented precision. The ability to predict the movements of comets and planets reinforced the idea that the universe was an orderly and predictable place. This deterministic worldview had a profound impact on various fields, from engineering and physics to economics and political thought. The belief in a predictable universe influenced how people approached problems and sought solutions. The principles of Newtonian mechanics were applied to understand and manage complex systems in society. Economists used these principles to model financial markets, while political theorists applied them to governance and social organization. The success of Newtonian mechanics in explaining a wide range of phenomena bolstered the belief that the universe was fundamentally ordered and predictable. This belief permeated many aspects of life, from scientific research to everyday decision-making. This belief, however, would eventually be challenged as scientists began to explore the frontiers of knowledge. New discoveries revealed that the universe was far more complex and less predictable than previously thought. The neat linear equations that so elegantly described the motion of planets proved inadequate when applied to the messy interconnected systems found in biology, ecology, and even within the realm of physics itself. These systems exhibited behaviors that were not easily predicted or controlled. Scientists began to recognize that the natural world was full of complexity and chaos. Weather patterns, ecosystems, and even the behavior of subatomic particles defied simple explanations and required new ways of thinking. While Newton's laws remain fundamental to our understanding of the physical world, they represent only part of a much larger and more intricate picture. Modern science continues to build on Newton's legacy, exploring the complexities of the universe in ever greater detail. As we delved deeper into the workings of the universe, we encountered phenomena that defied simple explanations. These discoveries have led to new theories and models that capture the richness and diversity of the natural world. We began to realize that the universe was not merely a collection of independent parts, but a complex system where the whole is often greater than the sum of its parts. This holistic view has transformed our understanding of the world and continues to inspire scientific exploration. The limitations of the clockwork universe model became increasingly apparent as scientists grappled with systems that exhibited surprising and often counterintuitive behavior. This model, which once seemed to offer a neat and tidy explanation for the workings of the universe, began to show its cracks. The more scientists delved into the intricacies of natural phenomena, the more they realized that the universe was far from a predictable machine. These systems, far from following a predictable path, seemed to evolve and adapt in ways that could not be explained by simply analyzing their individual components. The weather, for instance, with its chaotic patterns and sudden changes, defied simple explanations. Rivers, with their ever-changing currents and flows, demonstrated a dynamic complexity that was both beautiful and baffling. Consider, for example, the intricate behavior of an ant colony. At first glance, it might seem like a simple collection of insects, each going about its business, but a closer look reveals a highly organized society where each ant plays a specific role. Each individual ant operates with a limited set of rules and instincts. They follow pheromone trails, respond to environmental cues, and interact with their fellow ants in seemingly straightforward ways. Yet collectively, the colony exhibits remarkable feats of coordination and problem-solving. They build bridges with their bodies to cross gaps, work together to transport food, and even engage in complex farming activities. Ants build bridges, cultivate fungi, and defend their territory with a sophistication that belies their simple neural architecture. Their collective behavior is a testament to the power of simple rules leading to complex outcomes. This emergent behavior, arising from the interactions of many simple agents, is a hallmark of complex systems. Similar patterns can be observed in other natural phenomena, such as the synchronized movements of bird flocks or the intricate workings of a beehive. The stock market provides another compelling example. Here, the actions of millions of individual traders, each with their own information and motivations, create a system that is notoriously difficult to predict. Millions of individual traders, each acting on their own information and motivations, create a system that is notoriously difficult to predict. The market's behavior is influenced by countless factors, from economic indicators to human psychology. The stock market is not simply the sum of its individual investors. It is a dynamic, self-organizing system that exhibits booms, busts, and unexpected fluctuations. These fluctuations can be triggered by a variety of events, from political changes to technological advancements. These fluctuations are not random noise. They reflect the complex interplay of human behavior, economic forces, and global events. The market's movements are a dance of countless variables, each influencing the other in a delicate balance. These examples, from the bustling activity of an ant colony to the unpredictable swings of the stock market, highlight the limitations of a purely reductionist approach. They show us that to truly understand these systems, we must look at the bigger picture. To understand these systems, we need a new set of tools and a new way of thinking, one that embraces complexity and acknowledges the interconnectedness of our world. This approach allows us to appreciate the beauty and intricacy of the systems around us and to find new ways to navigate the challenges they present. Complex systems, despite their diversity, share a set of defining characteristics that distinguish them from simple linear systems. These systems are found everywhere, from the natural world to human-made environments, and they often operate in ways that are not immediately obvious or intuitive. These characteristics, often interlinked, give rise to the unique and often unpredictable behavior observed in fields ranging from biology and ecology to economics and social systems. The interconnectedness of these systems means that a change in one part can have far-reaching effects on the whole, creating a web of interactions that is both intricate and dynamic. One key feature is non-linearity. This means that in complex systems, the relationship between cause and effect is not straightforward. Instead, small changes can lead to significant and sometimes unexpected outcomes. In complex systems, the output is not directly proportional to the input. This non-linearity can be seen in natural phenomena like weather patterns, where a slight change in temperature or pressure can lead to vastly different weather conditions. Small changes can cascade through the system, leading to disproportionately large effects. This is often referred to as the butterfly effect, where a minor event in one part of the system can trigger a series of events that result in a major impact elsewhere. This butterfly effect highlights the interconnected nature of complex systems and the difficulty of predicting long-term outcomes. The interactions within these systems are so intricate that even a small perturbation can lead to a completely different trajectory. Another defining characteristic is emergence. Emergent properties are those that arise from the collective interactions of individual components within the system. Emergent properties arise from the interactions of individual components and cannot be predicted by studying the components in isolation. For example, the behavior of a single ant does not explain the complex and organized behavior of an entire ant colony. The behavior of an ant colony, the flocking of birds, and the human consciousness itself are all examples of emergent phenomena. These behaviors emerge from the interactions and cooperation of many individual agents, and the human consciousness itself are all examples of emergent phenomena. These properties arise not from a central controller, but from the collective behavior of many interacting agents. These properties arise not from a central controller, but from the collective behavior of many interacting agents. This decentralized control is what makes emergent properties so fascinating and complex. Sensitivity to initial conditions is another hallmark of complexity. This means that the starting state of a system can greatly influence its future behavior. Small variations in starting conditions can lead to vastly different outcomes over time. This sensitivity is what makes predicting the behavior of complex systems so challenging. This sensitivity, coupled with non-linear interactions, makes it difficult, if not impossible, to precisely predict the future behavior of complex systems. However, by studying these systems, we can gain insights into their patterns and develop models to better understand their potential trajectories. We can, however, study their patterns and develop probabilistic models to understand their potential trajectories. These models help us make informed decisions and prepare for various possible outcomes. These features, non-linearity, emergence, sensitivity to initial conditions, combine to create systems that are inherently unpredictable, yet often exhibit a surprising degree of order and self-organization. This paradox of order within chaos is what makes the study of complex systems so intriguing. Understanding these principles is crucial for navigating the complexities of our world, from managing ecosystems to addressing global challenges like climate change and economic instability. By appreciating the essence of complexity, we can better adapt to and influence the intricate systems that shape our lives. If you're interested in more topics like this, follow Mohammed Qasim Mahjani's YouTube channel.